All right. Okay. Thanks everyone for joining us today. We are doing a project presentation. And today we're joined by Dashel Mayers. He's going to be showing us some very interesting technical details. So I'll let him explain how that all works. But Dugan and Nikolay with us today in the audience as well. So just to feel free, anyone in the chat at any moment, if you have any questions, just pop them straight into the chat and we can ask our guest. But maybe Dashel, maybe you can start off by just telling us a little bit about yourself, and then yeah, you can share screen and tell us about these geodesics.
Yeah, hey. So initially I started this project it's like about a month ago. I got to the Wolfram Summer Research Program. We were all doing these sort of like short form presentations on projects we'd done in Mathematica in the past. So for that, I decided to present on geodesic analysis, which is sort of what I'm doing today, except I'm doing a slight extension because in that version, I only talked about how to find like geodesic paths and whatnot in Mathematica. Today I've extended it to include Desmos, as well as go over some like real world applications of why we'd use geodesics. I haven't implemented a couple of those in Mathematica yet, but yeah, I'll just walk through my project so far. So I'm gonna go ahead and share my screen. Let me know if you guys can see my screen.
Yeah, just give me a
Yeah,
second.
see it.
Zoom in a bit.
Yeah, so I want to like start off talking about like what is a geodesic? How are these things applied in the Wolfram context and outside of it in like the broader math community? So I think the crux of it is a geodesic is the shortest path between 2 points. Taking into account local geometry. So an example of this is, say, one wanted to get from one side of a field to another side of a field. In theory, the shortest path on that field is just a straight line through the middle of the field. But if the middle of the field is like swampy, say it rained, and the field it's just screwed up, so that might slow you down. So the actual shortest path, it might actually be going around the edge of the field. So that's kind of the local geometry element. Geodesics, I'll get more into their uses later, but they're useful for a lot of long distance travel. Particularly like for ships and airplanes, because they account for the curvature of the Earth. So if you see like transatlantic flights, they tend to go very far north. It might look like these flights, when they go north, it may look like a longer route on a map, but it technically is the shortest distance on a sphere. So you're actually using a geodesic to calculate your flight path, so to speak. In the Wolfram Physics project, I mean, I'm sure you guys can talk more about this than me, the Wolfram Physics project part, because yeah, you guys have done a lot on it. But I think in these examples, you're using it to find the shortest distance between 2 points on a hypergraph, I think. So you can also use it sort of on like coordinate geometry and whatnot. Here's the Wolfram Math World definition of it. So yeah, shortest. Well, okay, I don't really like this Math World definition, if I'm being totally honest, because it's not always the shortest line. It's technically the shortest path, but that's kind of like nitpicky. Yeah, I'd say shortest path between 2 points.
Yeah, line. I guess line doesn't have to be straight. Oh, right. But it says straight, right? Actually,
I mean, yeah, it's not really a good definition for me. Yeah, the straight line on a plane. Yeah, well, I mean, I'll show more examples of where it's not straight in like 2 seconds or so. But yeah, okay. So before I did this in Mathematica, well, technically after, because my first implementation was in Mathematica, I also looked into it in Desmos. So this is kind of, that's right. Let me see if this is. Can you guys? Oh wait, yeah. Can you guys see this?
Yeah.
Yeah. So this is a torus, just a parametric surface, and it's kind of showing like a point. Oh, it's like automatically rotating. It's a point going around this torus. Yeah, it's not a straight line, but it's just taking into account the curvature of the torus, find the shortest point around it. And what I did in Mathematica, I did this for a torus, a sphere, and a hyperboloid. I also looked at their Gaussian curvature. Yeah, there's just some notes that you can change around this to specify the initial point. I think it's a little bit glitchy as I go lower here. So I can go like fumble for a little bit, and then just the initial coordinates of it. This actually, oh yeah, didn't work. Oh yeah, now it's down there. That's kind of like, but yeah,
so it's kind of cutting into the volume of the torus.
Yeah, it's a little bit messed up, but it's plotting. It's essentially plotting the shortest path at this point can like walk, so to speak, across this surface of this. The path looks different for all sorts of surfaces, and I'll get into like the curvature on these different paths. It's, yeah, pretty reasonably soon. So getting into the mathematical implementation of it, yeah. So here I didn't show my code sort of. I guess I actually can pull up my code side by side because I have. It's kind of a mess up. All right. Yeah. So here are like the functions. I'll walk through what each one of these functions do. And then I can show you guys the actual notebook right after this. So torus params, since I have 3 shapes, I just say etc. because this does essentially the same thing. It's just defining the parameter of the shape. It's in the background here. So it's torus params, hyperboloid params, and sphere params. Yeah, it's defining the parameters for all 3 of these parametric surfaces. And what that actually means is it's generating the 3D coordinates that allow us to create the mathematical representations of these surfaces in 3-dimensional space. This second function, it computes the Kirchhoff symbols. So that essentially describes how a coordinate system is distorted.
If you have a notebook, if you have the notebook, I think showing the actual notebook and examples would be better if you have.
Oh yeah, I'll go into. Well, I have it right here, but it's sort of there's no actual explanatory text, so it's not that.
Oh, that's why you can speak and explain it.
Yeah.
Verbally.
Yeah. Yeah. So this right here, yeah, it describes how a coordinate system is distorted. And then geodesic equations right here is just the differential equations that describe geodesics on a parametric surface. So, and that, as I said earlier, it's just the paths of shortest distance on the surface.
Can you run them just to show the output? Because you can just show the actual equations, right? I think it's also.
I think I should. Oh no, this is. Do you mean like just call the function?
Yeah, on some parameters, like torus.
I mean, oh, it's all down. I mean, it's right here.
Yeah.
In this, but and then I have a slide analyzing like what this graphic actually means. But yeah, I can. Do you want me to skip to that, or should I walk through all the functions first?
Yeah, maybe.
Describe the functions and get to the
functions, their outputs. Like you have already a bunch of like curvature computed there. You can just show the output. We can read the output from the function.
It's like of a torus.
Yeah, well, just evaluate all the notebook, I guess. All the definitions above too.
It's I mean, let's see.
Just describe the functions, and if the notebook evaluates, that'd be helpful too.
Oh gosh,
just evaluate it as you usually do.
Just evaluate every single function in it. I mean, the output's the exact, or it should be the exact same.
You can just press like Shift Enter, Command Enter. You don't have to press that red button using your mouse. I think it's not the shortest path for your mouse to right. It's not a geodesic path to execute those cells.
Christ. And why does this work earlier and now it's a big mess? Naturally. Wait.
Well.
Now it's a mess. But in theory,
okay.
once this was evaluated roughly 2 weeks ago, you got this. And what this is just showing is the geodesic path on a torus sphere, and then here, this little image on the side is the hyperboloid, as well as the Gaussian curvature of it. And then here's just once you change the initial conditions, it's showing it as, it's the path with different initial coordinates. So as different points like walk around the surface, what's the path it traces? So the first path is the one in red. All the updated ones are the ones in blue. And what this essentially tells us, I have a slide on this right here. Let me share this again.
So your initial is like a point on a torus and a direction, right?
Yeah, exactly. It's just a point. That's what's explained on 1 second. On this slide. Oh wait, why did I just so many. Wait, how do I get back to Zoom? Share. Yeah, that's what's explained here. So you're just inputting, it's just a parametric function. And then given the point and the direction, it'll trace the path on the surface. And then this down here is just showing it for different initial conditions. So it's different points, it's different coordinates of the point that's being traced on the surface, on the same surface. Yeah, and then it's also showing the Gaussian curvature of it. So the sphere, it's very stable. As you can see, the Gaussian curvature, it's just sort of a straight line, one. Oh, wait, let me zoom out a little bit. Yeah, it tends to converge. The hyperboloid, that's on this. Can you guys also see my mouse?
Yeah.
Yeah, this column right here is the hyperboloid. Non-periodic, it tends to diverge and it's less stable. It's less stable because it's negative curvature, and then I'll get into like sort of what the curvature is later in the next slide. And then the torus, it can be periodic or quasi-periodic. Yeah, the stability of it varies depending on the region that you're in. Yeah, because there's certain regions that have positive curvature, and then certain regions of negative curvature, which impacts the stability. Yeah, here's sort of like what I derived at the end on the curvature. So when you're in an area of higher absolute curvature, it tends to deflect geodesics more strongly. And geodesics prefer to travel through regions of lower absolute curvature when possible. So yeah, I'm like on a torus, that would be possible because you have areas of positive curvature, negative curvature. On some surfaces, that's not possible. Geodesics are sort of like everywhere. A couple of examples I came up with and that are actually used in real life is, global navigation. I kind of brought this up like a couple minutes ago of transatlantic flights and whatnot. Yeah, they determine the shortest path between 2 points on the Earth's surface. So you use them for air and sea travel routes, like Great Circle routes in aviation. Yeah, you also do a lot of geodesics in fiber optic cable laying. Typically undersea communication cables will follow a geodesic path because that will minimize the length of the cable. And then that reduces signal loss when you've got a shorter cable and installation costs. So yeah, it's kind of all over internet infrastructure. And then there's also a bunch of like satellite positioning and for spacecraft trajectories because geodesics and curved space-time tend to show the optimal spacecraft paths. So I wonder if I can like just find actual images of these. And in structural engineering, I know it's for Jones. Yeah, so it's everywhere in structural engineering as well. They use it in domes because it shows the I think it's like the optimal load distribution. So yeah,
I'm actually curious about that transatlantic cable. Is there an image an actual path of that cable on the bottom of the ocean?
Oh god,
because it depends on the actual landscape.
It depends on the seafloor tomography.
I mean, yeah, it's gotta be. I wonder why it's still going this. Why is it not? I wonder if you can just say
maybe a sea cable.
Yeah, probably. Let's see. I mean, no. Oh no. I mean, I think that, let's see. No, it's not. Oh, now it's bugging me. Let's see. No, but it's not separate. No, this can't be right.
So the actual C cable.
This is separate. I wonder if this is the cables I'm actually thinking about, or if these. Oh gosh, this is crazy. But yeah, internet infrastructure, it's everywhere. I know that one of the Wolfram Summer, one of the people in our year did something, I think, on train paths. I think that they did. This is sort of related to geodesics. It's not a pain to find. It's disease modeling. Oh, flight paths. Oh, and train routes. Wow, those are really similar projects. But yeah, both of these are using like the concept of geodesics. And it's not just a straight line between them. I think it's technically not similar to underwater cables because you need to account for like the curvature of the seafloor. So it's probably and I assume that that's totally different than the curvature of the ground on land. But
I guess like in practice they introduce some kind of artificial curvature. Like on the actual land, there's a lot of problems that your train route can encounter, not just the actual curvature of the earth, right?
Yeah.
Maybe some city landscapes on the way, another kind of infrastructure that is on the way. So you can maybe potentially introduce like an artificial curvature.
So it'd be more interesting. But, okay, yeah, so then the train route would be more interesting because then there's less interference in the sky because that's just the curvature of the earth. But
what's interesting with that project is that
you can good plot if you keep scrolling down.
Let's see. That's a curious thing. It's over large.
Like with the flight paths, you could introduce something like wind as an additional vector that curves the space, and then calculate the geodesics based on how different things affect the curvature of your optimal length, shortest length.
Go down to the next one.
Let's see. Here?
Yeah, those plots, those 3D plots with the so they have the height field laid out, and they made that into a graph where the edge weights correspond to the differences in elevation. So this is choosing a path that minimizes elevation difference along the path.
That's actually
so this would be like the easiest train route if the train is because the train is penalized by having an incline.
Looks like
maybe they actually minimize some cost too, right? Probably.
Yeah, that's the cost function is the difference in elevation.
Like the actual dollar cost to lay out like 1 kilometer of railroad would depend on the actual position, depending on what is there. Maybe what would be all the infrastructure of actually delivering all the resources and all that to that particular position. So it's actually maybe the proper optimization has to also take into account that kind of cost functions.
Yeah. I mean, basically the cost function here is you have 1 unit of horizontal distance. There's the horizontal distance plus elevation difference.
I think it's also semi-related. I think that it's used in geodesics are also used in GPS systems. So I'm not. Let's see. Oh gosh. Oh, well, I guess that makes sense because you're just talking about navigation and whatnot, but oh no, I'm gonna get totally sidetracked.
I wonder what the origin of the word geodesic is, but it sounds very complicated, but it's just the shortest path. How did it come from?
It's, there's geo, which means, on land with the earth. And
the second
Geodesic.
part.
desic, I'm not sure. But
No, it's Geodesic. Accurately measuring it. Geometric shooting. I assume this came of.
Never seen
This
that word
field
before.
Yeah, it says that that's what's related to on the Math-World definition.
So let's once we looked at a bit of the history, maybe we should work on the notebook a little bit, see if we can resolve those things, and then actually play with some live code, see if we can maybe turn this into a half life science, and try to see if we can calculate the geodesic on a different shape. Is that going to be easy, or is that a difficult thing?
Well, I can hijack the live coding part, maybe, if you're not feeling comfortable. If you can send me the notebook, we can start it.
Right here. Oh wait, I want to try it as well, but do you have your Discord? Do I have your Discord? I'll try it on my own as well.
You're not on our Wolfram Institute Discord yet?
No, I am. I just don't know if are you Swish?
Oh yeah. Well, put it onto physics or somewhere.
Yeah, pop it into physics.
Yeah, I'll send it. Wait, I'll send it to your. Oh, wait, I'm in DMs. In the physics part.
By the way, for anyone watching, the Discord is getting nicely renovated. We're doing some full housekeeping, and officially, as of today, we have a full selection of new emojis that are available. So hand selected, appropriate, themed emojis.
Even Wolfram emoji or what?
Yeah, and a few more. So yeah, if you're not on the Discord yet, please feel free to join us, and there's going to be some interesting discussions about physics, philosophy, AI philosophy, that is. Some good topics that we selected for this year to work on. So yeah, excited to have the community participate in those discussions.
Wait, so let me try it.
Oh, you want to try it? I already started sharing.
Oh wow, no, I'm trying it on my phone as well, but
Just run.
It should be that.
See what it works. Yeah.
Hey. Oh, I was just no, I'm just
Let's try to fix it.
That's it. I was gonna try to do it on a catanoid, but yeah, we should probably debug the actual code first.
So can you explain so long while Nick is looking at the code, Dashel, what these different functions are here? What is each of these things doing? Like, for example, if we start at the top, you have a torus, you have a sphere, and a hyperboloid. So are those just different shapes?
Yeah, a torus and a sphere hyperboloid are different shapes. The functions itself are just they're supposed to be generating 3D coordinates for these shapes. Yeah.
So
that's those.
Okay, that's the top three things. And then the Christoffel symbols.
Yeah, that just computes the Christoffel symbols, which shows how a coordinate system is distorted, which then lets you formalize the equations in the next function. Yeah. And then geodesic equations. I mean, they're reasonably well named. That's just the differential equations that describe the geodesics on the surfaces, so on the torus, sphere, and hyperboloid. Then solve geodesic, it's just numerically solving the equations using our initial conditions. And then visualize, that's just the 3D plots showing the parametric surface and the curve on it. And that's like what's in the bottom columns of the visualizations.
So how's it solving for the geodesics? Is that a differential equation solution? What does it actually mean to solve such an equation?
Like, what do you mean?
Like there's it's using continuous maths or discrete maths. Like for somebody that's new to this world, how would you describe like what it actually means to find a solution? Is it just trying every possible path? Because normally if you think about shortest path from a AI machine learning perspective, there's different algorithms you can try, and it tends to be like an iterative process. So is it something similar going on here, or is there some kind of like different mathematical paradigm to solve these?
Well, it's continuous mathematics because it's so the params params is assuming a continuous parameterization of a surface. So it's for a function that maps from a continuous domain to a 3D space. There's also derivatives for the continuous functions. The metric tensor is computed using the dot products of partial derivatives.
Can we explain those couple words? So metric tensor. What is the metric tensor?
What is a metric? Do I not have like definitions of stuff?
It feels like an example here.
Just trying to break it down for newbies.
Well, it defines the geometry of a space. So it lets us measure distances, angles, volumes. So I think the more formal thing is it's a symmetric, non-degenerate second rank tensor.
Second rank, okay.
That shows how to measure distances and angles. In the space. And it allows us to calculate the lengths of curves, angles between vectors and volumes of regions.
So when you say tensor, it's kind of like how we describe a hypermatrix kind of multi-dimensional array that gives you different parameters with which to think about how curves in a space, like the distance of particular curves in a space. Is that an accurate way to reword
that's relatively that's relatively accurate.
So just as a random question, does gravity have an effect on the metric tensor? It's more like a physics question, I guess.
So like a metric tensor gives on a manifold, it gives a metric on the tangent space at every point. So you can have an inner product on tangent vectors at a point, and then you can use that to get the length of a tangent vector along a path. If you integrate that metric along the length of the path, then you have a way to have a measure of how long that path is on the surface.
So that's integration. That's like a continuous kind of mathematical difficult thing to solve. Right? That's normally quite a challenging mathematical calculation.
That's why it numerically solved.
I think that's what leads to I think it's gravitational time dilation. Is gravity's effect on a metric tensor. So totally. Let's see. Let me totally understand.
Yeah.
Oh, nice.
Fixed it.
Okay, so
I don't think I actually changed anything from when it was working to when it was not working.
Hyperboloid. Okay, so that's a hyperboloid. Interesting.
Yeah. But I wonder why the path on the
okay, so what's happening on the torus there? Like it's starting at that point on the right, and then it's kind of going up, and then it starts waving up and down.
Yeah. Wait, I wanna see if I actually got the.
And this one I want to start like here maybe. So
Yeah,
what
because
are the
when you did the geodesic for the hyperboloid, it kind of had this spiral instead of going straight
Yeah, it was
down.
math.
Is that because you're taking
It's
into
just
account some
something-
initial like velocity or momentum or something like that?
Wait, if you scroll down, you should be able to see what it should look like for the hyperboloid. It's at the bottom of the notebook, I think. Unless there's got.
Is that a hyperboloid or a column?
Yeah, there's the hyperboloid. It's that red line. It's wait, now it's rep, but yeah. I have it on my slides. Let me pull it up. Let's see.
So what are the initial condition here? Can we change the it's not like somewhere there towards the singularity, right? Somewhere like farther away. What's this? Kinda.
That kind of makes sense.
Oh, right. What the? Oh,
Okay, how do we change the angle? Is it like something similar? No.
what?
Hold on. We need to actually make sure that it's actually tangent, right?
I think.
What is A? Oh, A1. What are those parameters? Like UV. This is like angles. 0, 0. So can't I change it to something like this?
What does cos stand for? Oh, it's the cos of h. Cosine. I guess cosine h, cosine
No, that's hyperbolic ones.
hyperbolic.
Oh.
Yeah. So A is like a radius. Right, it's 1. It's just U and V. What this is. What are those parameters again?
I think,
I think the 30 is the length or the distance.
I think so.
Yeah, it's like something.
Yeah.
I think
yeah,
it's
that's
like
the length.
No idea how to turn it by different angles. Shoot. So straight.
That is
But that's not.
It's probably processing that
What?
number as a single entry somehow. It's not putting it into the parameters correctly, maybe.
It wasn't straight like 2 weeks ago with the same code, I think. It's supposed to. Let's try to send. See if I can. Why?
Yeah.
I can screen this and send it. This is, if you've seen the physics chat, this is what it looked like 2-ish weeks ago for the hyperboloid.
Looks like
The
this is the
torus-
tiny
Yeah.
there, right?
Oh, just make that
it's
thing.
not
Okay,
great.
now I get it. I wondered where it went. I was like, why is it invisible? So make that thing a lot longer. Make it like 10x it, Nick, and then see if there's some curvature starts emerging.
Well, it depends. You have your original parameters there. So I don't know.
Vigo 1000. The right scale now.
Yeah. kinda. Just do a random real. Maybe just then try a bunch of stuff. It's always it's like this.
I honestly don't think I changed anything between now and then though. So
Well, can you get a different geodesic on the Taurus?
Yeah, because the Taurus is also
That looks
changed.
interesting.
Mm.
Trying to figure out what's going
Yeah.
on there.
let me see if I can actually find my old notebook where this was working. Oh, I think it was.
Yeah, well, this one is different.
It looks like it's
Looks like it's trying to avoid that area of negative curvature in the middle.
Yeah, that was the initial note that I had on it was that I initially thought that geodesics refer to travel through regions of lower absolute curvature.
There it is.
Yeah.
Crosses the middle.
closer.
Yeah, those are much fun.
Huh. Oh, nice. So these are just random. Oh,
Oh wow. Yeah.
Random initial conditions.
Sort of going into the sphere, I mean the torus, the path.
What do you mean?
so our Taurus knots, PQ Taurus knots, are those geodesics?
Oh, what do you ask?
If Taurus knots, PQ Taurus knots are geodesics, or if that's only on the Clipper Taurus.
Hmm.
I guess I don't know.
Let me see. No, I think so. Some.
Yeah. Wanted to hack around.
Can you
Yeah.
unshow that table?
It's not really like. I don't think it's rendering that well. Like the path is going into the shape.
Really?
At the bottom.
Mhm.
I don't know. Let's do like 100 of them. It's basically gonna make a torus shape with lines.
Yeah, that's pretty cool.
Awesome.
Now just find the shortest path of those 100.
Oh,
How could you figure that out, Nick? Which of those is the shortest distance? Shortest length.
I think there's a.
I think they're all the same.
Oh,
It's
really?
it's just it's the same kind of parametric length, right? It's just
Okay.
different initial position.
Okay.
Right? That's how it's constructed.
I think that there's a function that you can do that like lets you do this much quicker or sort of quicker. Just find shortest path.
Well, find shortest path usually is for the graph.
Yeah.
Not surfaces. But I think that
fair.
some nice resource functions. Let's
Yeah,
try.
you could discretize the torus into a graph and then do it that way.
Look, there's a geodesic function. Looks promising. Alfred Drugay. I know like Alfred Gray have a lot of this kind of functionality for computing this nice geometric pictures and geodesics and curvatures. Look, right? So that's essentially what we did.
Yeah, basically.
So the way he encodes
Oh,
torus.
those flattened. Go down a bit to the flattened version. Scroll down a bit. Those look so much like Bohemian mechanics paths.
Yeah, what actually happens here? What has been plotted there? Oh, it's just a like flat projection of the two coordinates, right?
It's pretty cool to think about. That's the flattened projection of the torus, effectively.
Totally. There's some. I remember there's some fun name for those coordinates. The first one is like a toroidal, and another one is like poloidal. Toroidal and poloidal coordinates, right?
Pretty cool.
So this is like U and V.
So what's the green line then? What path is the green line taking around the?
No, it's just if one of them it's constant. I guess it's just like a
Either this way or this way.
Like this, right? Just not changing poloidal coordinate. Just a constant poloidal coordinate. Just on the top, for example.
But why? But you see, it's off, right? So it's like it's not, all of them cross through 4, 4. So they all have the same initial point, which means that constant circle must be. Yeah, it's interesting.
Yeah, well, they start with the same parameter. So the parameter is always from 0 to 4 pi. But U and V, just the parameters. It's like a time, local time something.
So, because you see how it always goes around the torus, like each of these lines that are blue, like it kind of goes around. So at some point it must unwind if it's constant somehow, or does it still go around the torus and somehow is constant? And my finger movements are so. So if we do that plots, that looks like a Krispy Kreme donut. Go back to the docs. There was that image a little bit up. So if you see this thing, right? Let me quickly annotate. Don't scroll when I annotate.
Let me plot. Okay. Make it larger.
Okay, so here's my question, right? Okay, okay, keep it still there. Okay, so here's my question.
Okay.
So you see how they're all going around the torus here and then coming around this way. So there's always like a full rotation around the outside. So my question is for that constant one, because all of the others kind of do something like this. For this constant one, how does it unwrap so that it stays constant on the circle like this?
Oh, it's cyclic. Those are always this is like a cyclic coordinates. Right? Look at the torus formula. If U is periodic, V and this is like a periodic formula, right? Maybe it has a higher period because you combine these trig functions together, so that its actual period is 4 pi, not 2 pi. But essentially, it like always returns to the same position when your t parameter goes from 0 to 4 pi.
Okay. So that's what makes sure it ends in where it starts.
Or maybe just 2 pi is enough. I don't know what was that 4 pi is all about.
But then the lengths would be different, right? If they start and end at the same point and there's different paths.
Well, it doesn't necessarily tell you that they should be different. Well, let's try to compute it. I don't know. This is like an actual equation for the geodesic, right?
Yeah.
So how do you compute the length now? Well, we can hack around it. First of all. So that's our end solve thing. Right, if this is our functions. Okay, what was the formula to compute the length of the curve? Is it like some kind of integral like this? Because I will forget. I am forgetting all of this. Is it something like this? Anybody knows?
Let me
Or
check.
some kind of derivative you want. You need to compute.
He's got
Maybe there's already.
llama, he's got llama 3.1.
Just gonna find. Oh, there's also. Oh, that's fine.
Oh,
Here's
there we
your.
go. Look at that. And so those still toruses or these? Oh, these are all different shapes.
They're different parametric surfaces.
So is there something special about them needing to be parametric?
I think it's a different thing if you do it on manifolds. Let me check.
Well, I know we can do like implicit region. I can't really represent it using an equation though. I think actually. Our metric region is fine. So as soon after we solve it, right? Like this is we essentially solved for ut and vt, two functions, and you solve values. So value. So this is like two functions depending on t. This is our parametric region. Right, I think that's how you can encode it.
So we want the formula for the length of a curve. Parabolic surface? No. Parametric.
Am I using it correctly? Or maybe more level list. You can make this plot.
Surface.
Okay, some kind of line. Well, if you can compute the line, we can do the region. What is it? Measure? How about discretize it first? Okay, this is like approximate length without doing any integration also. Okay, if we change different parameters, what is actually changing here for these curves? Or is it like the same curve? Right, it's just one curve.
That's one curve, yeah.
Yes, your starting line there that doesn't wrap around. So if you zoom in on that section on the left, I think you can actually see the starting point there. It's like over here.
What is this parameter for the geodesic? It's like that's the direction. You specify the direction with an angle. So give it a surface, your parameters, initial point, and initial direction, given by a single angle. So like I guess it's if it's always a 3D. I wonder how do you even specify it using a single one? You assume that you're always dealing with 3D surfaces, I guess. Right, so it's like an angle in the tangent plane in that point tangent to the surface.
Right.
So that's why it's just a single number. So this is just this essentially like a curves starting from pointing into a different direction. It's like it's drawn like this.
Can you just show one at a time there?
Show.
Oh, that's the surface of the torus. That's a parametric plot.
So this is like all the curves.
Are those curves in parameter space, or are they in 3D?
Well, so like the first one second one, so on. By itself, and doing this. I don't know why this is decided to hide it. I guess this is why.
Oh, wow.
Yeah. But if this is like your curves, do you saw it? No, this is your curves. The different curves. You can compute like a measure for all of them. Here. Make original those. I think. What? No. What am I doing wrong? Just returns all those list of pairs. Oh, it's not T.
It's multicolored curves. I think they're kind of like elastic bands, which would be a cool visualization because you can almost think about the elastic band trying to like contract and automatically finding the shortest path along the surface because it's trying to like get back to it's like most contracted form if they were stretched out, obviously.
Yeah. All right, so this is actually makes sense now. They're all different length, but it's kind of obvious because if you imagine the geodesic just around your poloidal direction, right? Just like going to be the shortest possible one when your toroidal coordinate doesn't even change.
If it starts and stops at the same point, or based on what?
Yeah. Okay. Just your fixed period of 2 pi, right? If you just 2 pi for both of those coordinates, one of them is just doing. This is like depends on the direction. One is going to be fixed if you're just pointing along like towards the center, so that it's just changing like that. One of them is going to be fixed, but
it depends on winding number.
Yeah,
on both axes.
Yep. So what would be the longest one?
It'll go this way. It'll be like infinite, basically. There would be a curve that never crosses the poloidal direction, right? Which would be going in the opposite.
No. There's no. It can't be infinite. It's always going to be because of we know that our equations are periodic, right? It's always going to return. So it's kind of obvious. It depends on the actual dimensions of the torus, but it's obvious that like the smallest one is that just like wraps around the poloidal direction, but the longest one is something like that's winding around.
It's winding, yeah. It's on.
Like this one.
Oh, because that's one curve. This blue line here, right?
Or is it like not obvious that it's like?
I think it's one curve. Can you zoom? Just make it a little bit bigger.
Yeah, it's one curve.
Yeah.
It's hard to see where the start is.
I'm pretty sure it's here. I think that's the starting point here.
Yeah, this is like the initial condition. Your direction. This is the initial point. Now let's make it 0. Yeah, what? That's not fun. How do you?
It's the plot region, I guess. It's the.
Yeah. What can I do? Plot range.
Plot range. There we go.
It's kind of very close. About just this. Okay, this is like obvious thing. If we do pi over 2, it's gonna be like this, right?
Yeah.
If we change one,
put it at 0. Okay.
About 3. Okay, that's pretty cool.
How much it is going? What's the actual t? It now okay. Okay, so this is like the maximum time.
Mhm.
So is it possible to actually compute the? So if you after you compute the geodesic, so this is like the when you have the equations, is it obvious what the actual period is of the solution?
Oh, well, I mean, sometimes they don't close up and they don't repeat. They don't come back around to the starting point.
Yeah, well, if your some initial condition is some irrational number, but if it's some rational, maybe it always repeats. Like pi, maybe, but what if like 1/3?
When did
Well, so like on the Clipper torus, like you get like periodic solutions if, so long as that angle is rational.
222/7. 22 divided by 7.
Oh, it's okay.
There must be a
Because-
disjoint there somewhere, right? Or no?
Maybe
Maybe it's just a little bit wavy, very slightly.
very close to pi, but not yet. Like if you're gonna let me so that I don't have to type it. But t max. Oh, look at it. What happens there? I think Indiesolve just broke. There's not enough accuracy to solve this for so long time. What if we just
What is it trying to solve there now?
we're trying to solve this
Mhm.
differential equation, right? Partial differential equation. Maybe I wonder what if we just increase precision, it's gonna help
Oh, wow.
or what?
Oh,
That looks interesting.
Not-
oh,
It's just sprinkles
I
donut.
know.
Like sprinkles.
Like after this step, it already starts breaking up.
Yeah.
A comment in the chat that you love it when a 10D plane plan comes together.
T equals 10,000 is.
Yeah.
I think it's-
Bring that down to like 100 or
Really?
10 or something. You don't run it for so long.
Oh yeah.
Also, it's
Yeah, it works with the
going
past.
one length at a time. I mean,
There's some you can play around with the like Indiesolve precision goal. Yeah, well, it even helps.
Angle.
Oh, there's no precision goal here.
Yeah, list of values, I think.
Oh, here. It's 10.
Mhm.
High accuracy and precision goal. Well, maybe we should specify both of these options. Oh, we're putting it in the wrong place.
The only position.
Here. Let me increase this thing. How about now?
Let's have a look at that.
It's like fun. I know. Yeah.
No,
Numerical
it's-
integration.
It's not a
Right.
donut anymore. It's some kind of croissant.
Actually, solve it
Some kind of bun.
precise. Maybe it's like has an analytic solution. Well, it's thinking, but I don't think it's gonna find one. Yeah, it's failed.
Oh.
It's failed.
So was that partial differential equation just like too much hard work, or is it too difficult?
no, it probably doesn't have an analytic solution.
Can you explain what that means?
I mean,
Also the-
something that you can write down as a function of like sines and
Yeah.
cosines.
or maybe some other special functions.
You can't know ahead of time because like the initial condition, the angle, I mean, it's you're trying to make it independent of the angle or have that parameter free.
I see. So what was it that we did that made it not have a solution? Potentially not have a solution.
But we tried
It's
to
trying to run it forever for 10,000 like time units.
There's a difference between dissolve and dissolve. This tries to solve it numerically, so that you can actually have to specify the range of time, like up to time step t, and this has to be also numeric, the direction, and it returns some actual numeric values of all the intermediate points as an interpolating function. It looks like there's some complicated oscillations going
Can
on.
you plot that?
Well, it's essentially the same. Here we try. And this accuracy group. So yeah, this is like the more the angle there.
So these are
the
numerical solutions.
0, pi. This is our initial condition.
Yes, that's cool. Very cool. So because it's numericals, that's what's given it that kind of like discrete, jaggedy curvature.
No, well, it's a dynamic optimization. I think when it tries to, I think it can be turned off somehow.
You actually it shouldn't be.
I don't remember how to turn it off, but there's some option.
It's like performance goal.
For the manipulate itself, or the underlying.
I think for the ND solve or whatever.
I think it's a actual
Performance
graphics
goal is for
the show.
try
Maybe. Those
quality.
No, still doing that. I remember there's a way.
But
to
that's
draw it.
Export them as like GIF or something.
No, put the performance goal inside the ND solve.
Well, dissolve is always exact. I think, right?
But I mean, that's just while you're moving it, and then it becomes.
There's no performance goal for this. Just like because we.
That's
yeah,
cool.
just for this parametric plot, not for the show. Overall, just for the one that contains the actual. This kind of.
Okay, so I want to say what does it look like the moment it goes, because this is just traveling around the surface. What does it look like the moment it goes around for the first time? What actually happens at that in between moment? So it hasn't crossed the center yet. So it keeps it basically.
Yeah, that's interesting.
I don't know.
Can you search for that moment, like what that looks like somehow?
Wow, it still hasn't crossed over. It's really interesting.
It's like they at the point they touch each other, they kind of like merge and then flip around. Something.
Something about the negative curvature which pushes geodesics away from it.
Oh yeah, so if you go again,
except for does it ever cross the center? I mean, yeah, if you head up around the small axis, you can go straight through.
Maybe you can search for it by creating a curve on the inside, which is that shortest path on the inside, and then just seeing when the curves cross.
Hold on. Hold on with your requests. Okay, one at a time.
So this is one idea. Just scroll up a bit. I'll annotate the donut. I'm gonna put some toppings on the donut. Oh, scroll down to the image. Yeah, okay, so keep it still. So I was thinking like if you had a curve on the inside like this, then what you could do is you could just check for the moment that these things get to the point that it actually like crosses the curve. And then that's how you'll know that that's the shape that basically is the first time that it touches.
Right.
But I don't know how you
Yeah.
would find. I don't know how you'd find this red. I don't know how you'd find this red one.
So when you change the angle, right? This is like your toroidal coordinate. You increase the angle. I think it starts to. It always goes up like this. It changes directions, which weird. This is just straight. I think it's like linearly, always increases linearly. That's interesting. It's this one is the. I guess we should always. Let me just focus on this V. Without caring too much. So just solve for V. Ignore everything else. Talk about it.
It says 6 Belarusio circles. Okay, never heard of that word before.
Okay, so if you do the same thing here, with some guess performance goals. So we'll help here.
So what is this plotting now? Oh, that.
It's just is it always like a sine curve? If it was just a sine curve, it would be. We should just check whether the sine curve is the solution for this.
Is that the flattened curve around the torus? Plotting it over.
This is one of the coordinates.
Oh, you see how it swapped over there? Did it swap over? Blue and the orange.
Blue is like, well, it has some slight variations from the linear. Looks like, right?
What's T now? Is that the length?
That's how long we integrate for. Essentially the curve itself, the position on the curve. That's how those coordinates behave. So like there's some waviness to it. It's not a straight line.
Increase the theta toggle. The theta, what is that thing? Theta O. See how they swap over?
Yeah. So it goes some point into the other direction.
Can you output the exact number of what that theta is, and we can see what that looks like on the actual torus?
Well, I guess it's just I think it maybe depends just on the initial derivative.
Oh, are these two the UV solutions?
Yeah. So if you solve it, so for you.
So what is U and V? Is that the two?
Those are the two parameters which take you around the torus. U goes one way and V goes the other way.
U and V. Okay.
Essentially, if you solve for initial thing, just essentially find the angle where this becomes negative. You can like do some kind of search. Define the function x or theta 0. Just numeric. I already have it. And so that just some number. Okay, we do the some kind of fine root thing when it crosses 0.
Okay.
And this. Guess you don't have to. Out. This
Okay.
weird.
Okay. So let's find that number. Let's look at that. Oh, I mean, like, what does it look like on the torus?
It's such a weird number.
Yeah, plug that in for theta.
Yeah, let me just try it. Just put here. It's like the moment it becomes.
Now show the Geodesic.
And this one again.
Wait.
That's
Oh,
Now show us 10.90.
no, is it just it's a? Can we just construct it? Is it the same essentially as? What is it divided by pi?
3.5.
Well, if it's periodic, then it's essentially like half.
It's just going around the small axis. Yeah.
So just a pi over 2, essentially.
So what did you solve for there? The shortest something?
I don't know, just whatever it switches this behavior, right? Where we're plotting it.
So I'm interested in that first switch, like when the orange and the blue swap over. I want to know what is that phase shift. Yeah, see, like that moment, that's like quite a big thing. Just completely swaps over. So let's put in 1.7 and see what that looks like.
Or is it?
Put in 1.7 and then
to-
1.71 and see what the difference is.
Okay, how do I search for it? Let's see the derivatives. These guys. What happens there?
Oh, something interesting happens. They touch. Okay, let's visualize that on the torus.
Yeah, derivative goes crazy at some point. How do you define it? It's some kind of square root of 2, I don't know. By something. For free.
Ah, maybe.
Maybe.
Scroll down, put it on the curve on the torus.
Somewhere in between.
Yeah, that's kind of that moment. Yeah, exactly. But,
So,
yeah.
so we need to find where it has roots. The derivative has roots, right? So like here's just always above 0, and then it just actually crosses it. So how do we find it? So again, it's like, and that's for the V, right? That's the second curve. I don't know what the blue one is doing. So it's like derivative of V as a, well, what if we plot the double one? This one. So what happens? Maybe it's more obvious. Not really.
And extend T a little bit more.
But it's like periodic behavior completely changes character. The hell?
the blue becomes faster than the orange. Faster, that's the right term. Has a higher period, more periods. Because look, it's like there's 3 and there's 1, 2.
No, yeah.
Yeah. So that's now the blue's got a faster and then go to below 1.7. Go below 1.7, so 1.6 or 1.68. Yeah. Okay.
Maybe like some Fourier components would help to catch that.
Oh, that's the same. Oh yeah. There we go. See that? See how they touch?
Yeah. Maybe
Yeah.
there's like the same thing.
That's like crossover movement. It's pretty cool. Okay, that was fun. Any suggestions from the chat? Dashel, this was your presentation. So anything you want to?
Hijack.
I'm gonna just like manually bisect it. Look, by hand.
I think it's.
There's almost like some chaotic behavior at that point. These curves are going all over the place around that. I'm pretty sure that's when, because you know how it like starts with a line around the, then it kind of like spreads out, and then at the point where they touch on the inside of the donut.
How is this number? What is this number? Just like a wild guess. I don't like this. But maybe it's not periodic like this. Maybe.
Pop that into the torus picture. Let's see what those look like as they go around the torus. See how cool it is.
So this goes to this.
Yeah, so basically, I think it started at 1.70.
170?
Yeah. That's already too much. So go to 169. Even that one's already crossing 168. There's like a moment where it hasn't started spinning round. Maybe even less. Let's just go to 1.5.
It's hard to catch what's happening.
Yeah.
I still wondering, like this is like the point of most interest, right? At least it's very visible on these plots.
I'm pretty sure it's that moment I'm trying to explain. Maybe my hand gestures are not working. Let's just try 1.5, and then we need to go off streaming in 5 minutes. But I wanted to explain what I meant by crossing V. Like in other words, at the moment where the V direction it's fully subscribed, that's what it feels like is creating this like sort of chaotic situation.
With me.
Because it's chaotic.
Like this thing is just. Hold on, where's actually? I lost it.
It's difficult. We don't even know what we're trying to solve for. Most interesting.
Well, are we trying to?
Most interesting moments.
Yeah. 9.
This is the hacker approach.
It is.
Yeah, I see what you're saying. Yeah, there's something interesting there. Okay, let's plot that. Let's plot that number.
So like very weird. Look at this, like it's close.
Oh, that?
I need plot range.
It's almost like an inverse shape there. Waiting each other or something.
So I could cross there, then shook.
Let's put that back on the torus, so we can actually take this back to the donut analogy. I'm good at comprehending food more than I am comprehending graphs.
What's that doing?
I mean, there's definitely some precision loss as you increase the length of the overall curve. It's interpolating the thing at a different get different behavior. Also, it's really interesting to change the initial condition, because if you start at the inside of the torus,
that's another way of doing it. Just change the initial condition. Okay, let's have a look at this. So you start off around the outside.
What we're doing. Well, that's what we're changing.
Oh, I see. Okay.
This is the initial condition.
I see.
What's the it's at a different point? Just right. Just well, it's 2, 0, 0 here.
It's one of the initial conditions.
It's just well, essentially we're trying to get what the hell is this number? Okay, that's like the main question at this hour.
That's your question. I want to know what it looks like. So what does that number look like when you put it into the torus? What does it look like?
I think it's like
there you go.
Oh, wow.
See how interesting that is? There's some crazy chaotic behavior there at that moment. I think it's the moment that the things cross over the minimal, the shortest v distance, basically.
Yeah, so like if you start in the center and you go like around the minor section, it shouldn't like deviate from that. But in the end you solve like it'll numerically like bounce out and then like diverge.
Interesting. So it's actually the end you solve that's giving it a bit of a chaotic initial condition or something.
Right. The way it's interpolating. Because it's taking like, oh, I want to go like 100 units. And so it sets up like interpolations at numerical points along the way. And then the divergence along that. So if you
do you think it's like the actual
you give it either like a
if you're gonna change integration methods, it's gonna matter? I don't think so.
This is the last experiment for today. Then we have to jump onto another.
Maybe it is.
But what we will do is we'll put a link to this notebook in the chat, and for those who want to have an excuse to start playing around with something, continue this experiment. So that's a lot more stable now, right?
No, I kept the same thing. I don't know. I still want to like just manually bisect it. Find the number. I don't know what. And then do the root approximate. Maybe it's just a simple square root of something. Who knows?
Okay, cool. Well, thanks for that. Thanks for prompting that session, Dashel. And it was really cool to see some geodesic analysis. Have you got any further directions that you're interested in taking this project or this research? Hey, Greg. Just one second.
Well, I wanted to try to actually implement the real world applications in Mathematica, like specifically the structural engineering one with the dome. I measured load distribution on that, but I didn't get around to it because COVID. Rip. But I think I'm gonna try it like next week.
Sounds good. I like it. All right, great. Thanks everyone for joining us today, and we'll catch you on the next one tomorrow. Okay. All the best for now.
Bye.
Okay.